and gentlemen, the topic we want to present today is solutions and solubility. Our presenter is going to be Latif. If somebody asks us how easy it is to keep physics as pet, I know our response is going to be that, oh, it is pretty simple. It is just a matter of getting the tank, getting the water, and the fish to be put inside the tank. But I want to tell you today that it is not that simple as one might think of it, simply because there are some dependent factors that keeping fish or survival of fish being kept rely on, because of the environment to which the fish must be kept. If anything happens to it, then the life of the fishes may be in jeopardy. Number one is the water that is going to be around the fishes. If the water is poisonous, which is very easy because of dissolved gases, ammonia is a case study that is generated from the leftover feed for the feces. If the feces ate particular food and the leftover is kept in that pond, ammonia is easy to come out and dissolve in the water, simply because ammonia is soluble in water. Water is very good solvent for ammonia, so it forms acid water, and that time the water becomes poisonous. That is why care must be taken when rearing fishes. The same way other higher animals, human being inclusive, we have learned that chlorine, fluorine, and other chemicals are useful in the treatment of water. Are used in the treatment of water simply because of their usefulness in the body. But again, what makes these gases to be beneficial is because of the quantity. If the quantity is too much in the water, then it becomes poisonous. In that case, the water is said to be poisonous. So what we are just trying to explain is the concept of solubility, which can make the environment to which a particular organism resides to be either necessary or deleterious. So we are going to take it step by step now, but before we go, I would like to go over our learning objectives. So today, after today's class, we expect that students will be able to distinguish between the different types of solutions. Then we are going to deduce that solubility is actually a function of temperature and some other factors, but temperature is much more important. Then we should be able to interpret the solubility curves and calculate the amount of a particular solute that can dissolve in a given amount of solvent at a particular temperature, because temperature is very, very important when we are talking about solubility. What is called a solution? We have talked about solution before briefly, when we said solution is homogeneous mixture when we have two substances present together, combined together homogeneously. So we said to have solution. Sometimes it is not only two substances, but majority of the times we have only two components of the solution. It is uniform throughout and contain majority of two components, as we have said. One of the components is the solvent, the other one is the solute. The solvent is that substance that has the other substance dissolved in it. When you dissolve substance A in substance B now, substance B is the solvent, then the other one being dissolved, that is substance A in our example now, is the solute. If on the other hand, substance B is being dissolved in substance A, then substance A is the solvent where substance B is the solute. What we're trying to say is this: any substance that is being dissolved in another one is solute, where the host is now the solvent. In some cases that we are going to be treating, water is going to be our solute, solvent rather, simply because of the universality of water. In such a case, we said we have aqueous solutions. There are many types of solutions. Here we say it's a mixture of gases that contains 79% nitrogen, 21% oxygen, 0.03% carbon dioxide. In that case, here is a solution of gases where nitrogen is serving as a solvent. We are going to see why it is like that. So when we have water and ethanol dissolve readily in each other, we have a solution of water and ethanol. So it now depends which one is solvent, which one is solute. But the bottom line is that the two are miscible, because in any proportion they are liable. They have the capability of dissolving each other. If we want to dissolve water in ethanol, or vice versa, the two of them are interchangeable and they can dissolve in one another. So in that case, we say that they are miscible. Then on the other hand, there are so many substances that do not dissolve in each other like that. We say they are not miscible. So the concept of miscibility or non-miscibility has to do with which one is higher than the other in quantity. In quantity, maybe water is more than ethanol, or ethanol is more than water. Anyone, according to this statement, anyone that is present in the largest or larger amount, depending on how many components are there, either by mass, or by volume, or by the number of mole, is the solvent. So in this case now, if ethanol is more than water, either by mass or in volume, ethanol is the solvent, water is the solute. But on the other hand, water is the solvent and ethanol is the solute. So anyone can be solvent, anyone can be solute. We can have solid solvent, we can have liquid solid, we can have solid solid, we can have liquid liquid. This example is example of a liquid liquid. Example of a solid solid is when we have alloy, like steel, when we have copper and carbon in iron. So when we have carbon in iron, iron is now the solvent, carbon is the solute. And again, we can have solid in liquid, like we have sugar in water, salt in water, like that. So those are just few examples of where we can have solutions, because ordinarily to a layman, when we say solution, we expect something like a liquid, but to a chemist, it is not every time that we have only liquid as our solutions. We can have solid solid, we can have any phases dissolving in one another. So the ability of a solvent now to dissolve a solute, there are some things that governs it. And the most important one is the force of attraction between the particles. When you have two substances that do not attract each other, definitely we don't expect them to be soluble, because they are natural enemies. But in the other way around, when we have something that are perfectly matched, that they can attract each other. That's when we have complete miscibility. The example is the case of ethanol and water that we have just said. Ethanol and water, they are friends. They can dissolve at any proportions because of the force of attraction. We have talked about hydrogen bond when we were talking about chemical bonding before. So hydrogen bond is the bond that is responsible for the solution of either water in ethanol, ethanol in water. The force of attraction is perfect, is very, very strong one, because both of them contains hydrogen bonding. So now solubility is now the tendency of a particular substance to dissolve another. That will be related to the amount of solute that is dissolved in a given quantity of solvent, mostly at a particular temperature, because temperature is much more important. So anytime we are quoting solubility data, we are going to be quoting them with number 1, temperature reference, number 2, a particular solvent, because at a particular temperature we have a particular solubility for a particular solvent solute pair. So if temperature changes, the same solvent solute pair, there is going to be a change in solubility value, because temperature is dependent on solubility and is very, very important. Number 2 is, apart from temperature that we have said, number 2 is the combination of solute solvent. A substance A and a substance B has a particular solubility. It is not going to be the same when you dissolve substance A in another substance C or substance D. So apart from temperature, and the nature of the solute solvent combination is another thing. So but the bottom line is that the solubility is the amount of solute that is dissolved in a particular solvent at that temperature. So now let us now try to see, to quantify there are some terms that are used when we are describing solubility. We said there are times that some substances are more soluble in some solvent than another. So that particular statement that is now guiding us to another concept of saturation, where we say a saturated solution is formed when no more solute will dissolve in a solution, and another solute is present. In that container where we have a solute and a solvent, a solvent has dissolved the amount of solute it is capable of dissolving. Even though there are more solute of that substance in the solution, it is not going to dissolve it, simply because it is saturated. So in another way of defining saturated solution is that it is a solution that contains as much solvent as it is capable of dissolving at that temperature. This doesn't mean that it cannot dissolve any other thing. If peradventure we have another solute in that system, it is going to dissolve it, but that particular solute to which it is saturated with, it cannot dissolve it again. Like an example now, solubility data of sodium chloride in water at 20 degrees is very, very common. It is 36 grams in 100 ml of water. So when we have a solution that contains 36 grams of 36 grams of sodium chloride in 100 ml, then that solution is saturated. So even in that container, you can have 200 grams of sodium chloride, it will not dissolve more than 36 since it is saturated. So now, if we now have another substance in it, it can dissolve another substance, but definitely not sodium chloride, because on sodium chloride at 20 degrees, it is saturated. If more sodium chloride is added to the solution, it will not dissolve, it will just settle down to the bottom of the container. Another one is the unsaturated solution. That is the complete opposite of saturated solution. No, sorry, it is just about to reach saturation. That is when a solution is not yet saturated. It contains less amount of solute that it can dissolve. It is like somebody that wants to eat food. Maybe you are hungry at a particular time. You eat a very small quantity of food that it doesn't satisfy you. That if you see another food or more food of the same nature, you are going to eat it. That is what is called unsaturation. So the same thing in solution. When you have a solution, you have a particular solute in that solvent. It contains that solvent, but the solvent is not enough, is not up to its required capability. So it can dissolve more when there are more solute in the solution. So at that particular point, when it has less solute that it can dissolve, we say that is called unsaturated solution, because if it's given some, it will dissolve. Like our usual example of sodium chloride in water. So if we know that the solubility data is 36 degrees, 6 grams in 100 ml of water. So if you now have 20 grams, normally it has ability of dissolving 36 grams. So to these 20 grams, we now make the solution to be unsaturated, because 36 is the required capacity. But if it's now dissolving 20 grams, then it is not saturated. It has more 16 grams that it's capable of dissolving. So the complete opposite of unsaturated solution is supersaturated. That is when the solution contains more solute than it can actually dissolve at that temperature. It's called unsaturated solution. So our example is 36 grams of sodium chloride at 25 degrees. So if we now have 50 grams of sodium dissolving in 100 ml of water, so we are going to see some crystals of sodium chloride in that water, because it has contained more solute than what the water can actually dissolve at that particular temperature. That is what is called supersaturated solution. It's just like human being that eat more than what it's capable of eating, so it will not be comfortable. Just like that for what we are discussing here. So the factor now, one of the factors that affect solubility, number one is the molecular size. For a particular solvent, because we have said that polarity is very, very important when we are talking about solubility. So when we have a solvent that can dissolve a wide range of a solute, let's take alcohol as an example: methanol, ethanol, propanol, butanol, and pentanol. All those, the first 5 series in alcohol series. So water can dissolve all of them because they contain hydrogen bonding. So now for molecular weight effect, now methanol is the simplest, followed by ethanol, then propanol, butanol, and pentanol. Methanol is completely soluble in water, then ethanol is completely soluble in water. So when you get to propanol, solubility reduces. It is not infinitely soluble, it is just ordinarily soluble in water. So when you get to butanol, the solubility data reduces to like around 9 grams in 50 ml at 25 degrees. 9 grams in 100 ml. So when getting to propanol, we have something like 3 grams. So it's reducing as the size of the molecule is increasing. That's why we said molecular size is another factor that affects solubility. Another one is the pressure. When you increase the pressure, you increase solubility. That is how the application is what is used in our bottled drinks. CO2 is pressurized inside the container to make it dissolved inside the container. So you can see that if you open the bottle of something, you are going to hear something like a sound and you see bubbles coming out. So when you have at that time you have reduced the temperature, the pressure, so the molecules have come out because they will not dissolve again when the pressure has reduced. So when the pressure is high, then they dissolve inside that solution. So where we are going is temperature effect. Temperature effect is not general like in molecular size effect and in pressure. It is not general here. It is the effect that temperature has on solid dissolving in liquid is not the same as when liquid is dissolving in liquid and when gas is dissolving in liquid. So let us check for solid first. In a solid, we said ordinarily the force of attraction determines solubility, how soluble particular substances will be. But now, to get into the interstices of the molecules of that solute by the solvent, we need to break the bond that is holding the solid together. So now, in solid, we need higher energy, very high energy, to break that bond. So if you want to dissolve more solute, you need more energy. So when you break the bond, you increase the solubility. So to break more bond, you need more energy. And temperature is a function of kinetic energy. According to kinetic theory, we have done that before. So thus, the solubility of most solid increases with temperature. So the example is that of caffeine in water. At 25 degrees, only 2.2 grams is dissolved in 100 ml of the solution. So when the temperature now increases to 100, the solubility increases to around 40. Like more than 20, as in 20-fold has increased by just increasing the temperature from 25 to 100. That is like 4-fold. So it produced the effect of around 40-fold, 20-fold rather. So that tells us that temperature is, for a solid dissolving in liquid, temperature is very, very important, because you need to break more bond to dissolve more solid. So to break more bond, you need more energy. To need more energy, that means you need to increase the temperature. So for liquid, the liquid is already present in that form that it can flow, such that we don't need to break that bond like that in order to have access to molecules by the solvent. So in that case, we don't need temperature, high temperature, in order to increase the solubility. So temperature has little effect on the solubility of liquid in another liquid. Conversely, in gas, the gas molecules are moving quickly before, and they have great deal of the kinetic energy. So when you now have a gas dissolved in a liquid, it loses its energy because you have confined it to a particular place. So at higher temperatures now, the gases that are trapped in the liquid before, when you increase the temperature, then you want them to gain energy. When they gain energy, then they escape from that solution. So that means you have reduced the number of molecules in the solution, then you have reduced the solubility of that gas in solution. So this particular temperature effect for gases is responsible for what is called heat pollution in water. So when the temperature of water increases, so the thing we know is that the aquatic organisms in the water, they will die. Then what makes them to die? We don't know it. So now let us now try to explain it. Ordinarily, we have oxygen dissolved in water. That is why we are able to see aquatic organisms surviving in water, because of the dissolved oxygen to be breathing in. So when temperature now increased, according to what we have explained now, the molecules will come out of the solution of the water, simply because they have gained more energy. They come out. When they come out, the amount of oxygen now reduces inside the water. Then the oxygen will not be enough for the fishes and other aquatic organisms to survive. So they die. That is why we said when energy increases for water, then aquatic organisms will die. So let us now try to see what we have just explained now on the interpretation of solubility curve and solve some problems pertaining to that. This is a typical example of a solubility curve where we see serious solvate, potassium hexachloride, sodium chloride, potassium chloride, ammonium chloride, ammonium nitrate is like this. This is gas, this is solid, this is solid. So we see that, yes, let us try to take this into our mind. When we are talking about solubility here, the reference is always on the amount of solute in a particular amount of water. Amount of water can be in 100 grams or in 100 ml. They are the same because the density of water is 1 gram per ml. So 100 gram and 100 ml of water are the same. So now we are going to see that all this solid, their solubility in water increases with temperature. This is temperature, the horizontal axis. So this one that is a gas, solubility reduces with temperature. And the same thing here. So now this is the interpretation of solubility curves. So we can be given a particular data on temperature axis. They will be asked to read it on the solubility axis. Anything we get there is our solubility. That is how to read solubility curves. So we can also combine solubility of different sorts to get at a particular temperature. And again, there are some calculations that we can do on solubility curves. So let us try to see things that we can do about solubility curves from the following examples. What mass of solute will dissolve in 100 ml of water at the following temperatures? Also determine which of the three substances is the most soluble in water at 15 degrees. That is a two-in-one question. The number one is the mass of solute that will dissolve in 100 ml of water. That is the definition of solubility. The mass of solute, the amount of solute that dissolve in 100 ml of water. So from this curve now, they are just trying to let us know the definition of solubility and to just trace it directly, because what they are asking us is particularly the question on temperature, and to trace it with respect to a particular salt on this axis. 100 ml and 100 grams are the same, as I've said earlier. So potassium nitrate at 70 degrees. Just go to 70 degrees. This is our 70 degrees. Where is potassium nitrate? This is the curve. At 70 degrees potassium nitrate. This is around 130. 130 is the amount of that solute, amount of potassium nitrate that are dissolved in 100 grams of water, and 130. So the same thing for sodium chloride at 100. So we go to 100. Where's sodium chloride? This on this is 40. Then ammonium chloride at 90. We go to 90 degrees. Where's ammonium chloride? This is ammonium chloride around 70. Around 70. Then which of the three substances is the most soluble in water at 15 degrees? At 15 degrees, we go to 15 degrees. this is in between the two here, is 15 degrees. So we go, so I'm out of these three: potassium nitrate, sodium chloride, and ammonium chloride. So potassium nitrate, sodium chloride, and ammonium chloride. So this is potassium nitrate, this is ammonium chloride, this is sodium chloride. I think the one that is more soluble is one that contains more that is present in the largest amount in water at that particular temperature. I think that is sodium chloride, because it is actually around 40. Yeah. If this is 40, around 40, so others are less than 40. So let us check our answers and see. 140, 40, 72, and sodium chloride. Yes, that is our answer according to what we have gotten. So what term out of this is saturated, unsaturated, or supersaturated best describe a solution that contains 70 grams of sodium nitrate in 100 ml of water at 30? So if we look at that curve again, 70 grams of sodium nitrate. So we are going to look at the solubility of sodium nitrate at 30. This is sodium nitrate at 30. What is the value? This is around 90 something, between 90 and 100. So it is able to dissolve between 90 and 100, let's say 95 degrees. So now that solution that now contains 70, is it saturated or not? So we are going to see that it is not saturated, simply because it can contain more than 70 grams. Then the second one is the solution that contains 60 grams of dissolved potassium chloride at 80 degrees. At 80 degrees, potassium chloride is where? This is potassium chloride. So it can contain about 50 grams. So now, when it now contains 60 grams, then what happens? It has contained excess. I think that is super saturated. So let us check our answers and see. Yeah, that is what we have just said now. So the third one now is we are to determine the molarity of a saturated sodium chloride solution at 25 degrees. So we look at that table as usual. Sodium chloride at 25 degrees. This is 30, this is 20, 25 is around here. It's around here. Sodium chloride is around here. It is not up to 40 grams because this line is, that small one top here is 40, then this line is around, let's say around 39 or 38. So I just choose 38. So it's about 38 grams of sodium chloride dissolved in 100 ml at 25 degrees. So what we need to convert now is, what is 38 grams in 100 ml in molarity? So just convert the 38 grams in 100 ml to something in molar unit, that is molar. That is how many mole will be in 1000 ml. So 100 ml of water contains 38 grams of sodium chloride. Therefore 1000 will contain that amount, that is 380. Then 1 mole of sodium chloride contains 58.5 grams. So then 380 grams will now contain how many? That is 6.5 molar. That is how to do the calculations, and I think we should be able to interpret more if we see more solubility curves and do some other calculations that are required us to do if we have studied these three examples, because they are actually relevant, because I don't think there's anything we have not touched with these calculations, although there are many ways they can ask their question. But the idea is, if we follow this, we are going to get almost all the questions. I don't think there's any question that can be hidden in anywhere apart from what we have discussed. So thank you very much for listening. We are going to present the concluding part of solubility, in the next class by the grace of God. So don't forget to share and like our video. Thank you for listening. God bless you. Really good.